So SU2 is a simple Lie algebra. So let's define another important concept, which is, now we know what an invariant subalgebra is, but we will also need an abelian invariant subalgebra. And when we do more examples, we shall see cases of these things. Okay. So an abelian invariant subalgebra is a subalgebra that commutes with the whole Lie algebra. Okay, and that would be an abelian. So do you know of? Can you think of an example? Of an abelian invariant subalgebra? Okay, let's refresh your memory. Remember the Heisenberg algebra? So the Heisenberg algebra had X, Y, and Z, right? And the commutator of X and Y gave me Z. But the commutator of X and Z gave me 0, right? And the commutator of Y and Z gave me 0. And obviously, Z will commute with itself. So isn't Z like a abelian invariant subalgebra then?
So it's like a scalar then? Some kind of scalar multiplied with the identity operator?
It's basically an U1 factor.
Oh,
so at the algebra level, in the group level, it's basically a U1 factor. Okay, so this is the, so usually, UN groups. So UN groups always has a U1 subgroup. And at the algebra level, this will have an SUN subalgebra and a generator for U1, but the U1 generator will commute with all of these guys, right? And that's basically would be an example of an abelian invariant subalgebra. These are like subtle concepts that it took me a while to, get a hang of, and even now, often I get confused. So it's only with time and with practice that you get used to some of these ideas. Okay, now the next definition, so I'm always giving you examples, is the semi-simple Lie group. Or semi-simple Lie algebra, sorry. For all of these algebras, there's a Lie group associated with them. Okay, so suppose you have a Lie algebra which it can have some invariant subalgebra, but it cannot have an abelian invariant subalgebra. Okay, so if a Lie algebra does not contain any abelian, this is very important, it's abelian invariant subalgebra, then it is called a semi-simple Lie algebra. Okay, so let me give you an example. I mean, part of it's in assignment 2, there is an example where you have to essentially, rewrite the Lorentz group SO1, 3. You have to find its Lie algebra. But the Lorentz group is can be analytically continued to SO4. And SO4 can be written in a way such that it is actually has two commuting SU2 factors. And that means it's a direct sum, meaning that they commute. Okay, so this is an example of a group which has invariant subgroups, non-abelian invariant subgroups, right? Because this SU2 will commute with this SU2. Okay, but it does not have an abelian invariant subalgebra. And therefore, the Lie algebra of SO4 is semi-simple. Okay, this is semi-simple, but it's not simple. Okay. Is that clear? Why is it semi-simple? Because there is no U1 factor. But why is it not simple? Because it has a non-abelian invariant subalgebra. Is it clear that it doesn't have a U1 factor?
No, sir.
Okay, so if you take an element, say from this thing, let's call it, say, GL, or like a Lie algebra element, let's call it, say, TL. And if you take an element from here, TR, then all elements from TL will commute with all elements of TR. Right? So this means that they are, so if I look at, so this means that it's an invariant subalgebra, right? So SU2L, it's an invariant subalgebra, right? Is that clear, Nahi?
Yes, sir.
Okay. And SU2R is also an invariant subalgebra. But for any of these to be an abelian invariant subalgebra, then elements of TL would also have to commute amongst themselves. But this is not true for SU2, right? So there is no subalgebra which is abelian, invariant subalgebra which is abelian. But there is an invariant subalgebra which is non-abelian. Does that make it clear?
Yes. So where does this U1 part comes in? Like,
so there is no U1 here. That's what I'm saying. There is no U1 or there is no abelian invariant subalgebra. Because there is no abelian invariant subalgebra, that's why it's semi-simple. But there is a non-abelian, there are two non-abelian invariant subalgebras. Right? This guy is a non-abelian invariant subalgebra. This guy is another non-abelian invariant subalgebra. And because of that, it is not simple. So SO4 is an example of a group of a Lie algebra which is semi-simple but not simple. So we can have semi-simple Lie algebras which are not simple, but simple Lie algebras cannot be semi-simple. Because SU2 itself is not it's not simple, right? So it is simple. Okay. So let me write that statement, okay? So semi-simple Lie algebras, don't have to be simple, but simple Lie algebras are semi-simple. Because if there is no invariant subalgebra, that also exclude abelian invariant subalgebras. I already gave you an example of a semi-simple Lie algebra, which is not simple, right? Which was SO4. Although we have not really explored the structure of SO4, just take it on faith that it is a direct product, a direct sum of two SU2s. And simple Lie algebras, which are semi-simple, is SU2. And the other example is UN. So UN is not semi-simple because it has a U1 factor, right? And similarly, the Heisenberg algebra is also not semi-simple, right? Okay. Any questions? Okay, so